Should we start? There's not much more room in this. No many more seats in this room available anyway. All right, welcome. Welcome to this lecture about cosmic structure formation. I could help you showing you a seat right here. So I'm a bit surprised by the resonance, by how many people there are here. And we have expected fewer people, and so we decided for this lecture hall. It's a bit crowded. It's now also a bit late to get another lecture hall. I hope you're fine with this. We are also recording this lecture. We are offering a stream. And if you want to, can you read this, or is it too small? If you want to have a look at the stream, you can find, well, first of all, do you know how to get to these pages here through the tutorial group system of the department? Okay. So if you go on the website of this lecture, you find the link to the live stream here. And I'm also going to record the lecture and offer the video offline. I don't know if anybody wants this. I don't know if anybody reads this, but mainly going to do is to describe an analytic theory to you that we developed in the past few years in our group here in the Institute for Theoretical Physics. I really don't see any free seat anymore. I'm sorry for that. In the front, of course. All right. So I want to describe a theory to you that is based on ideas of non-equilibrium statistical physics, and that has a lot of formal resemblances to statistical quantum field theory. I was trying to talk colleagues working on quantum field theory to give this lecture together with a course on statistical quantum field theory, but this didn't work out. In any case, I hope you're not going to be disappointed by what I'm going to present. As I said, it's only to a very small degree the standard approach to cosmic structure formation, and to a much larger degree different ideas. And as you will see, the different ideas will lead to an analytic understanding of many of the properties of cosmic structures as we observe them now. I wasn't sure whether we should offer a tutorial group. Who of you would be interested in A, solving problems, B, discussing problems and their solutions? That's going to be a small group. Very good. So we will offer problems, and of course you are free to have a look at them or not. And Selin Üstendal here is going to lead a tutorial group in which you will have the opportunity to discuss and present your solutions. But of course, this is meant to go in depth into some questions that we come across in the lecture, and to get acquainted with the formalism that you will see. Now, since the group of you who is interested in having a tutorial is rather small, how should we go about finding a suitable time? So excluded times are Mondays and Thursdays from 9 to 11. This is not possible. Essentially anything else is possible. When would be good times for you? Those of you who wanted to... Sorry? Right afterwards? Yeah, I was thinking about how would that be? Would that be okay? Right afterwards is fine by me, but the slight problem is that right afterwards usually we have an institute colloquium. If you don't want to attend, Celine, it's fine, of course. But right afterwards may be the best possibility to find a a suitable time. How about the others who wanted to take part in the tutorial? It's fine? Shall we start with that? We would start the week after next week. So you would receive the first set of problems next week, and then the first tutorial would start in the week after that. So that would be the week after October 30, well, of October 31st. Is that correct? I think it is. All right. Let's see how that goes. Now, who of you did already attend a course on cosmology? Quite a few. Did you discuss the general idea, the usual ideas about cosmic structure formation there as well? Would you mind going through them again? That's what I want to do today, because we will need the results of that in order to proceed. All right. These are my preliminaries. Is there anything else we should? Yes, about the time. We started at 2:15 today because that's how it's written down in the course book. But is that good or is it bad? Should we rather start at 2 p.m.? Need more time for lunch? So 2:15 is fine. I wouldn't like to start later because, as I said, there's a possible overlap with the Theoretical Institute colloquium. Okay, then let's start. So, cosmic structure formation. What is it that we want to understand? Obviously, we see structures in the universe. And with these structures, I mean, there's the solar system, there are many other stars, there's the galaxy, there are assemblies of galaxies, and there are huge arrangements of galaxies. And if we go very much back in time, we see the first image of cosmic structures in the temperature fluctuations of the cosmic microwave background. What is this? This is an image of the sky seen with radio eyes, or seen in the sub-millimeter regime. So if you take an image of the full sky, then of course you need to project it on the plane. If you project it on the plane, depending on the projection scheme, you get an elliptical image. So if you think of any point in this ellipse, it represents a point in the sky, and if you color this point with the temperature fluctuation that you measure there in the cosmic microwave background, then you get this image. The cosmic microwave background is leftover heat radiation from the Big Bang. Its average temperature is 2.726 kelvins, and what you see imaged here are fluctuations of the temperature above and below this mean temperature. And the color scale is such that the amplitude of these temperature fluctuations that you see imaged there is on the order of a few times 10 to the minus 5 relative to the background. So these are tiny fluctuations, right? About 10 parts in a million. This image is approximately, or shows the state of the cosmic material, the cosmic plasma, approximately 400,000 years after the Big Bang. And now, in the universe, now the universe is approximately 14 billion years old. So this shows the universe in an extremely early stage of its evolution. And we see structures pre-formed already there. And we see their fluctuation level. Now, this course is not about how these structures arose. We have certain ideas about how these structures came about. We are not going to talk about that. We are going to talk about how they evolve over time, because that's complicated enough. So what happens over time? What happens over time is this. This is now an image of the same sky, of course, because we only have one. But this is now taken in the infrared. So this is an image of the sky taken at 2 micrometer wavelength. The first one was in the millimeter wavelength regime. This is now the micrometer wavelength regime. And again, you see this, the full sky, and it's centered on its equatorial plane here is centered on the plane of the Milky Way. So this means that the projection of the plane of the Milky Way, right? We are sitting in the middle, so we only see the projection. The projection of the plane of the Milky Way falls on the equatorial axis of this image. So that's the north galactic cap, that's the south galactic cap. And what you see imaged there is that each individual point represents a galaxy whose infrared emission you see, and the color roughly encodes the distance of that galaxy from us. And I'm showing this image first of all in order to demonstrate the level of structures that we have today. That you have huge structures in the assembly or in the arrangement of galaxies, the apparent arrangement of galaxies on the sky. And the very simple question that we are going to pursue all through this lecture is, how do we get from here to there? This is the initial condition, or rather, we take this image as the initial condition, and we want to know how we can understand the formation of structures at this level after 14 billion years. And you can immediately see that this is impossible, and then we need to speak about the details. So the very simple question is how to get from here to there. Now, of course, this is a beautiful image, and you see an arrangement of structures in this image. We are not going to undertake the endeavor to understand these particular features on this map. Because this is a specific realization visible from that point in the universe that we happen to inhabit. We are not interested in the specific appearance of that particular image, rather we are interested in understanding the statistics of this image. Right? So we want to understand structures of what size occur in this image with what amplitude. Because understanding how the individual structures specifically look like is futile. Right? This depends on the specific realization where you find yourself within the universe. So suppose you sit on a boat on the ocean. We do not want to understand the specific pattern of waves, but we want to understand the statistical properties of these waves. How many waves are there of what length? How many waves are there of what height? This is the point that we want to understand. We are aiming at a statistical theory, or rather at a theory for the statistics of cosmic structures, not for their particular appearance. And this is, of course, different from numerical simulations, right? Numerical simulations, you want to follow one particular realization of structures. And it has advantages and it has disadvantages of doing it that way. We'll see about that. All right, and of course we want to see if I start with patterns that have this particular the particular statistical properties that we can read of here, then how can we understand patterns that have these particular statistical properties? That's the point. That's what we want to understand. Now, of course, you could say, and many people say that, why don't you just run a computer simulation and then you know everything? Well, the point is that you do not know everything then. I wanted to explain this as well, not because I want to ridicule or downgrade or whatever numerical simulations, because they have their own purpose. We have different goals here, and I want to explain what our goals are right away. Which of course have to do with a question, why are we looking for an analytic theory of cosmic structures in the first place, rather than a way of numerically realizing them? So this is the result of a numerical simulation, and you see the same kind of filamentary structures that you see indicated in this image as well. And if you go into a statistical analysis of the results of numerical simulations, you find usually very, very good agreement between the patterns that the numerical simulations reproduce and the patterns that you can observe in the distribution of galaxies on the sky or in other cosmological measurements such as gravitational lensing. It is relatively easy to understand why a filamentary pattern like this is expected to arise. And we go through that in the course of the lecture, because it's important for you to understand that the formation of filamentary structures like you see indicated here is not something special, but a generic feature of what we call structure formation in a Gaussian random field. But this is an old finding, right? This goes back to the 1970s when Doroshkevich found that whenever you start structure formation with a Gaussian random field, then you expect the formation of this kind of filamentary structures. But I want to show this to you because this is also one of the characteristic and analytic features of structural formation from a Gaussian random field. Speaking about Gaussian random fields, why is this so important? I want you to understand this as well. Why do cosmologists always refer to Gaussian random fields? Right? Why do we assume we have a Gaussian random field? What are the main reasons for doing so? This will also be part of the lecture. Right? Why do we start with a Gaussian random field? Why are filaments a natural outcome of structure formation beginning with a Gaussian random field? This is the kind of question that I want to address with this lecture. All right, suppose we understand where these filaments are coming from. Then the next thing we can look at are intersections of filaments. This is what astrophysicists or astronomers or observing cosmologists call galaxy clusters, right? These intersections. If you have a detailed look at them, and not only at galaxy clusters, but maybe also at smaller structures, then you see that they are self-similar to an amazing degree. Which means the following thing. Suppose you focus in on one of these structures. For example, this one, right? Conveniently indicated here in the center of this image. Suppose you focus in on that, and then you determine the radial density profile of the mass distribution within that object. In other words, you focus on the center. What's the center? A different question. Anyway, you focus on the center, and then you determine what is the matter density going outward in radius. As a function of radius, how does the density fall off? You determine the density profile, then you find that this density profile is essentially independent of the kind of object that you're looking at. A galaxy cluster, a galaxy, a dwarf galaxy. Over a range of approximately 10 to the 8, or a factor of 10 to the 8 in mass, this density profile turns out to be approximately the same. With modifications that we believe we understand, nonetheless, there seems to be a universal density profile in self-gravitating, so gravitationally bound objects in the universe, quite irrespective of their mass, so therefore quite irrespective of their length scale. Why is that? What is the reason for this universality? We don't know. And numerical simulations will never tell you why this is the case. Because numerical simulations just give you the result of the simulation, but don't tell you why this result emerges. And one of the main reasons why we developed the theory that I'm going to speak about is that we wanted to understand universal features in gravitationally bound objects in the universe. And I think we got a bit nearer to that, and since we got a bit nearer to that, I took the courage of giving this lecture. Anyway, but of course you might say, well, this is the result of a simulation. Who knows what the universe is doing? And why would the universe do the same as the simulation does? Well, let's have a look. This is a real galaxy cluster, a Bell 2263, as everybody recognizes. And a while ago, in a major project that I was part of, we wanted to address the also very simple question, what's the density profile of this galaxy cluster? Now, of course, traveling costs forbid just going there and measuring it. And measuring the density profile of a galaxy cluster is, in fact, rather difficult. It is easy as long as you don't get too close to the center. And it's also easy as long as you don't get too far away from the center. But if you want a density profile that goes from the center of these objects to the outskirts, you need to combine different ways of measuring the density profile. And this was the main aspect of that program that we followed up with. Yellow points are from strong gravitational lensing, whatever that is. Red points, green points, and so on are from weak gravitational lensing. These are methods to measure density profiles. And the blue curve is what you expect from the numerical simulations. And you see the result very clearly shows that not only the density profiles of objects that we can identify in numerical simulations as self-gravitating, but also real objects observed in the universe, in fact, do have the same density profile. Let me bring this as a motivation for the whole lecture. So we want to understand. We are aiming for an analytic theory because we do not only want to reproduce features of cosmic structures, but we want to understand their fundamental physical reasons, right? Why do they attain certain universal features? Yeah.
How many galaxy clusters have been measured?
In that way, with that precision, about 30 by now. And you do see this universality, yes. But of course, that's an important question, right? If that was the single one we found, you might raise doubts. But it turns this is very, very costly, right? Because you need to observe with a space telescope the innermost parts of the galaxy cluster, and you need to observe with ground-based telescopes the outskirts because the field of view of the space telescope is way too narrow to cover the whole thing. Then you need to adapt the two ways of measuring, and so on and so forth. So this is very costly, right? We spend approximately a third of the observing time of the Hubble Space Telescope of a whole year in order to observe these galaxy clusters, but the result is really stunning. I'm showing you a pretty example here, admittedly, but the others are not much less pretty. All right. Mm-hmm.
I'm wondering how much those two answers that we set out are actually at odds with one another, because if you usually talk about universality, what you mean is actually kind of an independence of the underlying theory. So, in what sense are we talking about probing the real physical properties?
That brings me to the second point. The next question is, of course, which of these features do depend on what aspects of the cosmological background? On the type of dark matter, possibly on the amount of dark energy, possibly on the theory of gravity, and which of them are completely independent? This is another important aspect of asking these questions to an analytic theory and not to numerical simulations. Because we also want to see, is that a particular feature of that particular realization of the universe that we happen to inhabit? Or is it more general than that? Does it depend, does this density profile, do these universal properties depend on how the universe expands specifically? Or is this just a consequence of the universe expanding in the first place, no matter what? Is that specific for general relativity as a theory of gravity, or is it more general? Does this happen specifically with the type of dark matter that we believe surrounds us, or is it independent of the type of dark matter? So we also want to address this kind of question. And if for any aspect of this question you want to run a numerical simulation, you become a pretty old woman or a pretty old man in doing that. With an analytic theory, it may be easier. Yes? Louis, you're coming late and then you start asking questions. What is this? Go ahead.
Maybe you could expand a bit on the actual difference between running a numerical simulation and solving equations numerically, because how is it different solving, like solving an equation numerically, where you also need to specify the initial conditions if you do it dynamically?
Okay, that's an important question, but I would like to postpone that and postpone it to the time when we will start about the foundations of the theory that I'm going to talk about. All right, is this enough for a motivation? All right. That's what we want to understand. Goodbye. Now we go on the blackboard. What are we going to do now? I'm going to speak a little bit about the cosmological standard model. I'm aware that, of course, very many of you have heard about this already, and others did not. Well, let me summarize the main features that we are going to need in the course of this lecture, and let me then go into the standard picture of cosmic structure formation. This has its limitations. Nonetheless, we need certain features of that. Now, what is the cosmological standard model? It's in fact very simple. It's the attempt at describing the evolution of the entire universe with a physical theory. If you want to do that, you need first of all to specify on what physical theory you want to base this model, and then what further assumptions you want to make about the model in order to specify the theory further. Now, there are three assumptions entering into the cosmological standard model. Number one is we use general relativity as the theory of gravity. This may or may not be wrong, right? But we have good reasons to believe that general relativity is at least very close to the theory of the gravity that we experience. Whatever it is, we start with this assumption. General relativity is the basic theory that we build our cosmological standard model upon. The other interactions do not matter for constructing the overall picture of the universe, because they are either short-ranged, like the strong interaction or the weak interaction, or they can be shielded because of opposite charges, like electromagnetism. So gravity alone it is, and we stick with general relativity in order to describe gravity. Second assumption is the universe is isotropic. Wait a moment. Wait until it's dark. Look outside. Of course, the sky is not isotropic. This is not what we mean. What we mean is that if you measure certain average properties of the universe, such as the temperature of the microwave background, the average number density of distant galaxies per solid angle on the sky, or properties like that, those turn out to be at least almost direction independent. Now, there is one good reason that I showed you already to believe that the universe is in fact isotropic about our position in the universe, and this is the cosmic microwave background temperature fluctuations themselves. Right? I showed you this image. I told you that the fluctuation level of the temperature about its mean is on the order of 10 parts in a million. This is not isotropic, but it's almost. Okay, suppose you buy that. Wait a moment, it's not true. It's not true if you observe the microwave background with an actual telescope. Well, suppose you have 250 million to spend, and you buy yourself the appropriate satellite, and you observe the cosmic microwave background with that. You will see that the cosmic microwave background is far from being isotropic. But this is because we move with respect to it. If you move through the rain, you get wet in the front and less wet in the back. If we move through the cosmic microwave background, we see the cosmic microwave background, because of redshift, a bit hotter in the direction into which we are moving, and a bit cooler in the direction from which we are coming. This is not what I mean, right? This is a particular feature of our position in the universe. If you remove this so-called dipolar feature of the cosmic microwave background, then you get this image that I showed you, and then the cosmic microwave background is as isotropic as you could hope it to be, 10 parts in a million. All right, but this only shows that our cosmic microwave background is isotropic about our position in the universe. How about other people? Communication is difficult across the universe. So we assume that everybody else at any other position in the universe would observe the same thing, isotropy. This is pure speculation, almost pure speculation. We don't really know whether this is true or not. You can ask the question whether you could, for example, represent cosmological data in a better way if you assumed that the universe was isotropic about us, but not about everybody else. These are locally isotropic model universes. And then you will find, and we did this experiment in our group, then you will find that the data do not prefer this. Right? In fact, the data are in better agreement with assuming that the universe is isotropic not only about us, but about our neighborhood as well. So we have these three assumptions, right? General relativity, isotropy about our position, and everybody else has the same rights. A universe that is isotropic about everybody is homogeneous. So sometimes you see these assumptions also summarized as, one moment, general relativity plus isotropy plus homogeneity. But this is mathematically the same thing as saying isotropic about one position plus isotropic about everybody else. Yeah, Luis.
How well do we manage to stay away from cooking up circular arguments here? Especially if you think about maybe the dynamics of the universe has some attractor which makes it look after a long time of evolution isotropic. And we don't really know what this dynamic is, or what these dynamics would look like on a more fundamental level, or maybe by that find if the solutions display some generally attracting solutions. And if we look at something like the cosmic microwave background now, we want to also go back in time, not only move around in space. So is this, how much is that maybe hidden in what we are going to do?
All right, let me give a pragmatic answer and a more theoretical one. The pragmatic one is, these are the assumptions we are making for now, and we are building our theory upon that. If you see any discrepancies with data, you should rather think about your assumptions. If you don't, you're happy. That's the pragmatic approach. The less pragmatic approach is, if we do indeed live in a locally but not globally isotropic universe, then the region surrounding us, first of all, which may have lower or higher density than the average, must be centered almost upon us, because otherwise we would see a dipolar feature in the cosmic microwave background, apart from that created by the motion of the sun. And if this local region of isotropy would not be very large, it would be in conflict with a measurement of the expansion rate from type 1a supernovae. So it's a fairly safe bet. But maybe you should not bet your own money on that, but somebody else's money. Anyway, these are the three assumptions we are making. Right? And if you want to test other assumptions, okay, the result of actual empirical tests so far has been that there is no evidence for us to deviate from these assumptions. All right, then what do you do? Well, I should specify more precisely, first of all, If we speak about isotropy and homogeneity, I'm speaking about spatial homogeneity and isotropy. You could also speak about, or you could also speculate about homogeneity in time. It's a very interesting speculation. It would mean that the universe would not change over time. This was the origin of the steady-state model of the universe, an ingenious model which then turned out to be wrong by observation. And so we are limiting isotropy and homogeneity to spatial sections, three-dimensional sections of the universe. All right, if we do that, we get a mathematical expression for the metric of space-time, of cosmic space-time. We insert this metric of cosmic space-time into the Einstein field equations, and there are two equations remaining, the so-called Friedmann equations. And this is what I'm going to write down now. So the Friedmann equations specify how, well, I should start differently. One of the fundamental observations that we make in cosmology is that galaxies fly apart. Right? So if we observe galaxies in our neighborhood, by far the majority of those is moving away from us rather than towards us. And if you eliminate galaxies that are very close to you and only look at galaxies that are distant from you, you see that all galaxies are moving away from us with a speed that increases with distance. This is the fundamental observation of cosmology. Now, if we insert an ansatz for the metric that incorporates the symmetry assumptions that we have made into the Einstein equations, we get two equations. Y2 is a different story. We get two equations for one function, namely the function describing how the separation between any 2 points in the universe is changing over time. And if the universe is expanding or shrinking, given the assumptions that we have already made, this expansion or shrinking must not depend on the relative orientation of these 2 points, because that would violate isotropy. And it must not depend on the actual position of one of these points, but only on the relative separation of these points, because otherwise we would violate homogeneity. So the only thing that we can quantify is, if I pick up any 2 points in the universe, how is their separation going to change? And given our symmetry assumptions, this way of changing must not depend on where I am and into which direction I'm looking. So there must be a unique scalar function that tells us how any 2 points in the universe move apart over time. Now there will be 2 equations left. Well, Y2, because the Einstein field equations describe the time-time component and the space components of the metric. There can't be any space-time components because they would define a vector and that would violate isotropy. But nonetheless, there must be one equation that comes from the time-time component of the Einstein equations. But the space-space components of the equations must all tell you the same thing because of isotropy. So for the space-space components, there must be one equation. For the time-time component, there must be one equation. So therefore, there are 2 Friedmann equations. All right, what do they look like? Well, suppose A is the function I have been talking about. It's the function that tells you how any 2 points in the universe move apart or towards each other. That's a function of time, of course, and it must not be a function of spatial coordinates, because that would violate isotropy or homogeneity again. So this is one. Let me explain the symbols first. The function A we had. A dot is the derivative of that function over time. If you have been exposed to general relativity already, you know that time is an observer-dependent concept. nonetheless, making the symmetry assumptions that we have made, turns out that there is a single cosmological time, a preferred cosmological time coordinate. That's the time I'm talking about. All right, that's the density of whatever there may be gravitating. That could be ordinary matter, that could be dark matter, that could be photons, that could be neutrinos, elephants maybe, I don't know. K is the spatial curvature. What does that mean? See, if we have a preferred direction in time, we have a preferred way of identifying 3 space. It's everything perpendicular to that direction in time. K is the curvature, could be positive, could be negative, or could be 0. Right? The spatial curvature. It's measured to be 0 anyway, so this is going to disappear from the equations very quickly. And lambda is the cosmological constant. Cosmological constant, well, anyway. That's the other one. Now here, one additional symbol appears. That's the pressure. Now, as you know, pressure is a form of energy density. We compare here the pressure to the rest energy density of everything else. And this is why we usually neglect pressure in cosmology altogether, at least in the late phases of cosmic evolution. Even if matter is very hot, right, the thermal pressure is extremely low compared to the rest energy density of everything else in the universe. So usually we are going to neglect pressure anyway, and then this is going to disappear. So these are the 2 equations that we obtain from Einstein's field equations, and these are the equations that we are going to deal with. All right. In your cosmology course that some of you had, did you speak about the cosmological constant and why you need it? Did anyone tell you about Lovelock's theorems? Mm-hmm. Anyway, it's there and we need it. All right. Now I'm going to multiply the second equation by 6a dot, just for the fun of it, right? Not 7, not 5, 6. So then we have 6a dot a double dot equals minus 8 pi g rho plus 3p over c squared times a dot Okay, that should be correct, yes. That's true. Okay, thanks. Good. Now, what else can we do? We can multiply the first equation with a squared and then take a time derivative. So if you multiply this with a squared, then you only have a dot squared over here. You take the time derivative, you get 2a dot, a double dot. I want 6, so I multiply it with 3, okay? So I take this equation, multiply with 3a squared, and then I take a time derivative. All right, then I'm getting here 6a dot, a double dot. And of course you see it coming. The idea is to later subtract these 2 equations. All right, I multiply with 3a squared, so I have 8 pi g rho a squared. I take a time derivative, so I get 16 pi g. Let me write 8 here. And then I get 2a dot. That's from here. I multiply with a square. I multiply with 3. I take the time derivative. It's gone. Because it's a constant. Multiply with a square. Multiply by 3. So I get lambda c square a square. I take the time derivative. I get 2 lambda c square a dot.
What about the special dependence of the density? The central dependence?
That's adding to it, yes. Of course. Right, we're here. So we multiplied with 3a squared, so we get plus rho dot a squared. Thank you. And then plus 2 lambda c squared a dot. Yes. Indeed. All right, now let's subtract the first equation from the second. Then the left sides are going to vanish. The cosmological constant is going to drop out. This means that in both